Hello everyone, and welcome to the Support Vector Machines Project Solutions lecture. In this lecture, we're going to be going over the solutions for the Support Vector Machines project. Let's go ahead and jump to the notebook to get started. Okay, so here I am at the Jupyter Notebook. Let's go ahead and get started with the solutions. So I'm going to scroll down to the first task, and the first thing we wanted to do was to use Seaborn to get the iris dataset by using iris equals sns.load_dataset iris. Let me go ahead and import Seaborn in order to do this. So we'll say import Seaborn as SNS, and we'll go ahead and copy that line. Iris equals SNS load dataset, and we pass in iris. And that will load the dataset for us. So just a quick note, Seaborn has its own datasets, and we've seen things such as the TIPS dataset before. We'll go ahead and just use Seaborn to load the iris dataset. And we're going to import some libraries we think we'll need. And basically this is just pandas and numpy. And set matplotlib inline in order to actually see the visualizations for the exploratory data analysis section. What we're going to do is create a pair plot of the dataset. And there's a question attached to this: which flower species seems to be the most separable? So I'm going to say SNS pair plot, pass in iris for my data frame, and then I'm also going to specify the hue to be by the species column. So if we actually take a look at what iris looks like, we have sepal length, sepal width, petal length, and petal width, and then a species column. And I'm going to use that column to actually color my data. And I'm going to go ahead and change the default palette to dark 2, just so it matches the solutions notebook. And if you go ahead and run that, you'll notice that in most of the features, pretty much all of them, it looks like this green class of species is really separable from the other two. And that's going to be the Setosa class. So Setosa is highly separable. Pretty much any machine learning algorithm should be able to separate this easily if it's a competent algorithm. We're going to go ahead and also create a KDE plot of sepal length versus sepal width for the Setosa species of flowers. So in order to do that, I'm going to set a object called Setosa, and that's going to be the iris data frame, where the species column was equal to Setosa. And then I'm going to say sns.kd plot, and then I'm going to pass in Setosa. If we go ahead and check this out, pass in on the x-axis sepal width. So we can go ahead and say Setosa. We can actually just pass in the whole column if we want to. Sepal underscore width. For y, we're going to go ahead and pass in Setosa sepal underscore length. And then I'm going to set the CMAP to plasma, just so it looks a little nicer. And I will say shade is equal to true, so it shades in. Let's go ahead and run that. And let's not shade in the lowest value, which is this dark purple. In order to do that, I can just do shade underscore lowest equals false. And then I get a plot that looks just like what we had in the solutions. So kind of a tricky plot. You had to separate first the data frame in order to use Seaborn to do this. But if you were having trouble with this, don't worry too much about it. It doesn't have much to do with the project. It was kind of just something to practice your Seaborn skills with. Now let's go ahead and move on to train, test, split. We'll go ahead and split our data into a training and testing set using scikit-learn. I'll go ahead and say from sklearn.cross_validation, import train, test, split, run that. And then from train, test, split, I'm going to go ahead and just grab that default example that we always use right here. Then I'm going to pass it in. We'll go ahead and just use random state is equal to 42. Not a big deal in this case since the data set's pretty small. I'll set test size equal to 0.3. And then I'll specify x to be my features, which is just everything minus the species column. That's going to be along the axis equal 1. And then y is going to be just the species column itself, what we just dropped. Let's go ahead and run that. And now we have our train test split. Let's go ahead and train a model. We want to call the SVC model from sklearn and fit the model to the training data. So we're going to say from sklearn.svm import SVC. And then I'm going to go ahead and say SVC model is an instance of SVC. And I'll go ahead and fit that model with its defaults of the training data, xtrain and ytrain. And you get a model with the default c equals 1, gamma is the string auto. Okay, now let's go ahead and grab predictions from the model and create a confusion matrix and a classification report. I will go ahead and say predictions is equal to svc underscore model dot predict off of the x test data, so my test features. And then I'm going to import from sklearn metrics my classification report and my confusion matrix. Then I can just say print confusion matrix comparing y-test to my predictions. And I get something that looks like that. And if it's different from the answers, don't worry about it. That's probably because of a different random split in your data due to the train test split. And then I'm going to go ahead and call a classification report on y-test and my predictions. Okay, and it looks like we're doing pretty good. We've only mislabeled 2 of them. We'll go ahead and see if we can improve this, and this is going to be really hard because it's a pretty small data set, and we can only work with 2 here. And this may change depending on what you used for the train test split as far as what your random value split was. But let's go ahead and see if we can practice using grid search. So the data set's quite small. You probably won't be satisfied with these results in real life, but let's go ahead and continue on. We'll go ahead and say from sklearn dot grid search import. In this case, I want grid search CV, and we'll go ahead and create a dictionary called paramgrid and fill out some parameters for C and gamma. I'll say paramgrid is equal to, we have a dictionary, and let's pass in some values for our C value. We'll go ahead and do one similar to what we did in lecture, 0.1, 1, 10, and 100. So just by powers of 10 there. And then we will say gamma and pass in some values here. We'll say 1, maybe 0.1, 0.01, and 0.001. Okay, so we have our param grid, and what we will go ahead and do is create a grid search CV object and fit it to the training data. So this is going to be 2 lines here. I will create a grid search CV object, pass in SVC as the model I want to use, param grid as my param grid, and I'm going to go ahead and say verbose is equal to the number 2. So I see a little bit of output, but not as much as 3. And then I'm going to go ahead and fit this to my training data. Run that. And it'll run pretty fast depending on how fast your computer is, but the data set's small enough that this shouldn't take that much time to run. And then we'll go ahead and do the exact same thing as we did before by creating grid predictions with grid.predict off my test set underscore test. And now let's go ahead and try that confusion matrix again. We'll say confusion matrix, pass in y-test and my grid predictions. And you'll notice we did a little better here than we did with the default parameters. We were actually able to improve it by 1 classification. So our confusion matrix is going to be a little better, and so should our classification report. If we go ahead and pass in y_test and predictions. And we can compare this classification report to the default parameters up here for a classification report. Overall, both models did fairly well, but it's definitely important to practice how to do a good grid search using scikit-learn, especially when you're dealing with real-world data. Okay, hope you enjoyed the project. It's really just an exercise in making sure you learn the syntax for using grid search and, as always, calling a model from scikit-learn. If you have any questions, feel free to post to the Q&A forums, and the other students and I will be happy to help you out. Thanks everyone, and I'll see you at the next lecture.